Okay, so last class we talked about stacks and queues. We didn't go into too many examples of why we use it. I mean, a queue hopefully is somewhat intuitive, like with your printer, you set up a queue for it to print all the different jobs. But we didn't go into a stack too much. The stack is actually an incredibly useful data structure, but it's not always seen nowadays due to our new computing systems. One very common way it was done in the past, and hopefully this will help you understand some of the advantages of a stack, is how we used to do, or how we used to create calculators. So, okay. I guess we'll leave that up there. All right, so for example, in math, right now we do something called infix notation, where you put the operation between the two operands, so A plus B. That's how you add two things. You evaluate from left to right. But if you need to establish precedence, you have to use parentheses in order to override the precedence. All right? Right, so you remember, was it, please excuse my dear Aunt Sally or something like that? All right, good, they still teach that. Not this, did y'all have to do Common Core math? No, good, drives me nuts. So prefix or Polish notation, the operators are written before the operands. So A plus B becomes plus AB. All right, and this is like a function. The function is plus, and you add the two. All right, hopefully this isn't too crazy. Parentheses can be omitted. Hey, why is that?
Because you know that you're going to join them to
come next, right? So the precedence is encoded in the way that you do it. The other way you do it is called reverse Polish notation, and this was proposed by, ooh, good, we got some Australians. And then a computer scientist, the advantage operators appear in the order required for computation. So you're pushing numbers onto a stack, and then when you push an operator, you pop the operator, the two numbers, and then you do the evaluation, put the result back on the stack, and you're good to go. This has the advantage of it's a very simple data structure or way to evaluate it. Hey, look, there's some examples. So, go ahead and give me some simple mathematical infix. Did not call an equation. Expression. There we go.
A times B.
8 times, let's do numbers.
Okay. 8 times
3 plus 4. All right. So multiplication happens first, and then this one over here. The way you would write this, so, but if you wanted to do the addition first, am I recording on the board? Great. You'd have to do that, correct? Yes. Correct. So, but in order to do this in reverse Polish notation, you just do 8, 3, 4 plus multiplication. The reason for that, and let's go watch it, what happens on the stack. We start at 8, so we push the 8. We go to the 3, we push the 3. We go to the 4, we push the 4. We see a plus. When we see the plus, we pop the two elements, the 3 and the 8. We do the operation, 3 plus 4, so that means 7. And then we pop the result. I mean, we push the result. Then we see multiplication. So we're going to pop the two numbers again, do the multiplication, and we push it back on the stack. And then technically, if you write an equal sign, that means just take the top result and print it. Okay. What's the advantage here? Why? We're just going to talk about this today, not code it. This is I'm not going to expect you to write this calculator, but it's very important for you to understand why this was so important. Why was this preferred over that?
less memory.
Less.
Deallocates the memory of your copy.
Okay, yeah, deallocates the memory. What do you have to implement in order to make this happen? Well, here's the problem. Let's go over here. Let's see, so you have a multiplication. You have an 8. Then you have, oh, it's a parentheses. which then is going to have another child, which is plus, which will then have a child 3, another one 4. So we need to, oh boy. Anyone want to code this up?
Not really.
Not really? How about this? Is that simpler?
Probably.
Probably. This is just an array. When your computer didn't have much memory, you could only store so many numbers. You just created a stack of those numbers, and then you just started writing them, pushing them on the stack and popping them. As long as you weren't trying to hold more than whatever number of numbers could be stored on the stack, your calculator was good to go. Over here, you'd have to create a tree structure, which we haven't talked about yet, and then figure out the correct order of evaluation, because it's infix notation, and then go from there. So yeah, this is way easier, and also for when your hardware was not very complex, think 60s, 70s, and to some extent 80s. This was used all the time because of it. Naturally, calculators are more can take care of this, and with the 90s, we had enough hardware to make this easily a reality. But for a long time, we used a stack. And this is still used for other things. For example, when your function is being called, we call it a stack, because it is a stack data structure, right? You just push all your elements on the memory stack, and then you pop them when you're done. So it's still the stack is still well used a lot, and it's actually optimized in hardware for a lot of your computers. Oh wait, I'm erasing. How are we doing here? Doing okay? All right. I think that shows why a stack is useful, so let's go ahead and start.